Welcome to today's explainer, Structural Engineering Team. Look, we are pitching a solution to a headache you probably face every single day. We're examining a true next-generation material that survives exactly where your traditional ceramics just completely fail. If you're tired of dealing with components that fracture under thermal shock or just degrade under heavy mechanical wear, well, you're going to want to pay really close attention to silicon nitride, or Si₃N₄. Okay, so here's our roadmap for today. We have a lot of ground to cover. We'll be taking this material all the way from its bottom-up chemical synthesis to how we achieve densification, the gas pressure sintering mechanics, its unique microstructure, and finally, how it dominates in extreme thermal and high-wear industrial applications. Let's dive right in. Starting things off with Section 1, the silicon nitride advantage. Let's set a baseline here. We all know traditional structural ceramics basically hit a wall when pushed to their limits under extreme mechanical and thermal stress. Think about standard industry alternatives, right? Like alumina or zirconia. Alumina might give you medium toughness, and sure, zirconia offers decent strength, but when you compare them to silicon nitride, the differences are honestly staggering. Silicon nitride delivers excellent thermal shock resistance, and its mechanical strength jumps to very high. It doesn't just compete with the standard options, it fundamentally outclasses them in pure endurance. Now here's another massive advantage for this team: superior machining damage tolerance. In your world, precision is literally everything, and you need tight tolerances. Silicon nitride boasts significantly better machining damage tolerance and high-temperature reliability than both alumina and zirconia. What does that mean for you? It means when you're shaping these components for highly specific industrial geometries, they actually hold their structural integrity, instead of developing those annoying microscopic flaws that inevitably lead to catastrophic failure later on. Moving right along to Section 2, powder synthesis to densification. So how exactly do we get these crazy macroscopic properties? Well, we've got to look at the bottom-up engineering flow. The creation of a fully dense component follows a very strict sequence. It starts with powder synthesis, often using carbothermal reduction. After that, we introduce highly specific sintering additives. Those additives melt to form a liquid phase, which finally allows the ceramic to achieve full densification. Let's zoom in on those additives for a second, because honestly, they are absolute game changers. Silicon nitride all by itself is notoriously stubborn to densify, but by adding sintering aids, things like yttrium oxide, aluminum oxide, magnesium oxide, or even various rare earth oxides, we fundamentally change the game. These additives form liquid phases at super high temperatures. It's this liquid phase that basically pulls the particles together, enabling full densification. Without them, you'd just be left with a porous, weak block of material. But, of course, translating this into modern fabrication methods, like additive manufacturing or 3D printing, brings some real headaches. The material's covalent bonding and low self-diffusion mean you need incredibly high sintering temperatures. And because of that, strict shrinkage control is absolutely vital during densification. If you can't control that shrinkage, you completely lose the precise structural geometries your engineering team just spent weeks designing. Which brings us to Section 3, gas pressure sintering mechanics. So, how do we actually clear those high-temperature hurdles for commercial viability? Well, most industrial silicon nitride relies on a process called gas pressure sintering, or GPS. Here's the catch. At the extreme temperatures required to densify, silicon nitride actually wants to decompose. By applying a high-pressure nitrogen atmosphere, GPS essentially forces the material to stay intact. It completely suppresses that decomposition while it reaches maximum density. And the payoff for using this specific sintering process? It's exactly what your structural engineers are begging for. GPS allows us to achieve incredibly high density and outstanding mechanical properties. We aren't just throwing around buzzwords here. This is validated by rigorous flexural strength data and a very high Weibull modulus. That means its failure rate is highly predictable and incredibly reliable. In short, GPS guarantees the absolute structural integrity you need for your critical zero-failure parts. All right, Section 4, microstructure and fracture toughness. We've talked about how it's made, but I want to pose a question directly to the team to understand its internal secret sauce. We all know ceramics are brittle by nature, right? It's just a fact. So why does this specific ceramic exhibit such unusually high fracture toughness? How on earth does it survive impacts and mechanical stress that would just shatter alumina or zirconia into a million pieces? Well, the answer lies entirely in its crystal structure. Silicon nitride exists in two vital phases. First, you have the alpha phase, which dictates the initial densification. But during that high-temperature sintering process we just talked about, there's a crucial phase transformation. The material literally shifts from the alpha phase to the beta phase. And it is this beta phase that dictates the grain morphology and ultimately the final incredible toughness of your engineered component. As it makes that shift into the beta phase, it forms these unique, elongated, needle-like beta grains. Think of these acting like microscopic rebar inside concrete. When a crack tries to form and propagate through the ceramic, these elongated grains physically block it. They cause what we call crack deflection, forcing the fracture to actually change direction and lose its energy, and crack bridging, physically holding the material together. This is the toughening mechanism that gives silicon nitride its almost unheard-of durability for a ceramic. Let's switch gears to Section 5, dominating extreme thermal environments. Let's look at the macro scale now, 1400 degrees Celsius. Just wrap your head around that for a second. That is hotter than volcanic magma. And this isn't some theoretical laboratory number. This is the reality of extreme thermal environments, like industrial furnaces and molten metal processing. Silicon nitride doesn't just survive here. It operates flawlessly, without catastrophic failure, even under immense thermal shock. Inside these crazy environments, silicon nitride essentially plays two main roles. First, as thermal system components. Here, its primary job is functional, providing structural support right in the hot zones or facilitating heat transfer. Second, it's highly prized as custom insulating components. In this role, its specific job is to actively block heat transfer or provide electrical isolation, all while effortlessly maintaining its mechanical strength. So where do you actually use it? You're going to find silicon nitride totally dominating in induction heating fixtures, burner nozzles, thermocouple protection tubes, and molten metal handling. Why? Because it provides that essential thermal isolation and almost entirely prevents thermal cracking in systems that undergo brutal rapid thermal cycling. Where other standard materials just crack and degrade, silicon nitride stays completely stable. And finally, Section 6, High-Wear Industrial Applications. Let's bring this pitch home because, it's not just about the heat, it's about friction. The breadth of research on silicon nitride today is absolutely massive, but one of the most exciting areas is tribology, the study of friction and wear. Research consistently proves that these ceramics dramatically outperform standard alternatives in environments that demand extreme wear resistance. For you guys, this translates directly to your heavy-duty applications. We're talking high-wear industrial bearings and precision cutting tools. That's where those elongated beta grains we talked about earlier step in to prevent catastrophic material failure under friction. It's also quickly becoming the absolute gold standard for EV motor insulation and semiconductor plasma equipment, where parts have to resist wear while providing perfect electrical isolation at super high temperatures. So I want to leave the engineering team with this one final thought. We've seen the microstructural data, we've seen the extreme thermal endurance, and we've talked about the unparalleled wear resistance. If your current structural materials are failing under thermal shock, or if they're constantly cracking under mechanical wear, isn't it time to engineer your next critical component with silicon nitride? Seriously, it is time to stop constantly replacing failing parts and start building with the ultimate structural ceramic. Thanks so much for joining me for today's Explainer.